How's it going, everybody? This is Ron Sparkman from OpportunityU.com, and in today's interview, we're going to talk with my good friend Moriba Jah, who is at the University of Arizona doing the SOBS mission, which we'll talk about in just a little bit. But first up, let's bring on Moriba and say hey and get a little bit of his background. Moriba, how you doing, sir?
Hey, how's it going? Good, good, good. Thanks for having me. Yeah. So when it comes to who I am and kind of what I do, I am by training and education an astrodynamicist. So astrodynamics is the science that studies motion of objects in space. I got my bachelor's in aerospace engineering from the university, from Embry-Riddle Aeronautical University in Prescott, Arizona. Then I went to grad school, got master's and PhD, also in aerospace engineering at the University of Colorado at Boulder, and I focus on astrodynamics. Now, I fell in love with astrodynamics is because while at Embry-Riddle, one of my mentors, Professor Ron Madler, who's still there now, the Dean of the College of Engineering, when he was a student, he spent a few summers at NASA's Orbital Debris Program Office at Johnson Space Center in Houston. And so he worked on space garbage for some time, and he's the one who kind of turned me on to this idea of space debris and why these things behave the way they do in space. So he also went to Boulder for grad school. Now, after I finished at Colorado, I got a job as a spacecraft navigator at NASA's Jet Propulsion Lab in Pasadena, where I mostly focused on navigating Mars missions. So I worked with a great team of folks and really got into the nuts and bolts of understanding all the different forces that act on man-made objects and how that drives their motion. And I can tell you that, very small forces, if you don't take these things into account and you're trying to get to Mars, you could miss the planet altogether. And, very small accelerations build up huge error over long periods of time. And it takes about 6 months to get to Mars. So initially, if you don't take into account things like, the heat escaping the spacecraft surfaces, that sort of stuff, that's a significant error over the period of months. So I was able to kind of hone in and fine-tune my skill of being able to understand and predict how man-made objects in space behave. And I was at JPL for 7 years. My last mission was Mars Reconnaissance Orbiter. And then I went to Maui. My wife had a thing for getting to Maui, and it turns out that the Air Force Research Laboratory has some facilities on Maui, some nice telescopes that track man-made objects in space around Earth. And so I was able to get a job there as the lead astrodynamicist for the Air Force Research Laboratory, doing work on space situational awareness, space surveillance, and mainly really trying to understand and quantify and predict the behavior of objects in space.
That's an incredible resume, for sure. And I know one of the things that you really talk about whenever you do a lot of your talks around the world is really about being a space garbage man and really trying to figure out these things. And Jeff Bezos talks about putting millions of people in space, and of course we all heard a few weeks ago with Elon Musk talking about wanting to have 1 million people on Mars by 2100 or shortly after that. What's it really going to take for us to get there, especially when we're talking about all this debris that is really in space right now? A lot of people don't realize just how much there is that's out there with satellites that have been destroyed, and the pieces are out there just kind of floating around, and they're kind of doing their own thing. And it's something that only a few people are experts at, like yourself. So what is it that we can do to kind of fix this problem?
Right. So let's talk a little bit about what that problem is. I don't like being an alarmist. I like being more of a realist. So the sky is not falling right now, sort of thing, even though, about 1 to 3 objects per day from space kind of re-enter, but most of those burn up in Earth's atmosphere. But we don't have an impending doom problem right now, but we're certainly on the way there. I mean, right now, the Department of Defense, through U.S. Strategic Command, has developed and maintains a catalog of about 22,000 objects, the size of a softball and larger, and in different orbital regimes, different altitudes, including where human spaceflight currently takes place, where the International Space Station orbits. And out of those 22,000 objects, about 1,200 of those work and everything else is trash. Now, these are dead satellites, spent rocket bodies. Every couple of years, things collide with each other, and so those create more debris, more smaller objects, that sort of thing. You got nuts and bolts. So there are a variety of things that are man-made that comprise that population of debris. The bad news is that the 22,000 objects that I spoke about, even though these things, some of them are crisscrossing each other and that sort of stuff, those are only the trackable set of objects. We actually detect apparently lots and lots more, but we can't seem to track these things well. And so that's part of the crux, is that we don't fully understand all of the things that are up there and how they're behaving and what orbits they're in. And we can only track a subset of all these man-made objects. And so we need to do a better job with tracking everything up there as much as possible, and then really trying to understand these things in terms of the risks and the hazards that they pose. And once we can get our arms around that, then I think we can start moving towards what actual solutions might look like.
And that's kind of what you're really working on at the University of Arizona with SOBS. So can you tell us a little bit about this initiative and really what it is you've been working on? I know it has you traveling the world as well. I mean, this is obviously something that everybody's paying attention to. So could you give us a little background on SOBS and what you guys are up to?
Absolutely. So before I left the Air Force Research Lab, I was the lead for space situational awareness in the Space Vehicles Directorate. And part of my job was, from the Department of Defense perspective, really trying to understand what up in space could be a threat to defense-related space services and capabilities. Now, I think, writ large, everybody who has something that's operating in space wants that thing to work and to work optimally and to not be degraded or not be lost due to some collision or something else. And so, that kind of seeded this whole activity outside of AFRL. I realized that there's only so much that I could do within the government, and academia provides a great place to explore the art of the possible and be able to do so in a very unconstrained fashion. And so this whole space object behavioral sciences, that doesn't really exist as a science in and of itself. It's something that I just kind of made up less than a year ago, because one of the things that I noticed is that it's not, astrodynamics is really focused on the motion, but there are other behaviors that these things have that are not explained simply by, how the space environment interacts with different materials and shapes and sizes of things. Case in point, some people have come to me and said, "Hey, Moriba, can you tell me what the intent of that satellite is over there?" And it's like, yeah, the answer is easy. It doesn't have intent because it's not a sentient being. So if you want to understand, if you want to understand how actively controlled objects behave, those are obviously controlled by humans. And so you have to have some understanding of culture and that sort of thing to be able to kind of explain some of these behaviors. I can tell you right now that across planet Earth, it's obvious to everybody that we all don't behave the same way. Where we were born, where we're raised, the culture that we're in, that certainly drives the sorts of behaviors that we have, the types of holidays that we celebrate and that sort of thing. And so the funny thing to me is that invariably people, for whatever reason, think that everybody in space needs to behave the same way, because space is kind of a place where you do science and that sort of thing, and you got physics, and so because of that, everybody's going to do things similarly. And I can tell you that's not the case. If people want to understand, for instance, what's American behavior in space look like, something very interesting is if you start looking at when people maneuver satellites around, jostle them around in different orbital locations and that sort of thing, by and large, those things don't happen on holidays or weekends or Fridays or Mondays, because holidays and weekends, that's time off. Fridays, you don't want to try to do a maneuver before you go home for the weekend, and if it doesn't, if it doesn't work out right,
that's great.
Then you got to stick around longer, and you certainly don't want to come fresh from a nice weekend at home with your family to then have this pressure of having to do a maneuver. So most maneuvers happen on Tuesdays, Wednesdays, and Thursdays, and that's how Americans behave. But that doesn't mean that people from India necessarily have to behave that way, or people from Russia or China. So the thing is, there's a cultural input into some of the behavior of some of the objects in space, and that's why we kind of created this whole idea of space object behavioral sciences, is really looking at what are all the different things that play a role in how objects behave. I mean, even policy, one of the guidelines that exists to try to mitigate further debris, say in the geostationary region where we have a lot of our communication satellites, is after you have the end of life of your satellite, kind of remove your satellite from that orbit, raise it into what they call a graveyard orbit. And there's a specific equation that kind of governs or provides a guideline for what that graveyard orbit needs to be. So, because people put things in that orbit, now there's a behavior of objects that's driven by the location and the fact that they're in this graveyard orbit. But that was driven by policy. And so even policy and geopolitics in dictating or driving certain aspects of behavior of man-made objects in space. So that's what space object behavioral sciences is fundamentally trying to find the best ways to quantify, assess, and predict the behavior of objects in space, whether they be natural or man-made. But certainly the man-made piece is not just action of space environment with the objects themselves. Human beings have an input.
That's amazing to think of. Whenever we're talking about all these objects in space, you just kind of assume that they're kind of doing their own thing, and that there isn't really as much. It doesn't really have as much to do with us or the people that are operating in anyway. That humans are really such a massive part of what's going on. In fact, most people would just assume that they're doing whatever they want to do. We're going to set this, it's kind of going to go and do its own thing. And when you put that together and kind of realize that it's it kind of makes it an entirely different animal than what most people would assume. And I know that this has really kind of been taking you everywhere. You've been traveling a whole lot, and you're kind of trying to get this message out there. So can you tell us a little bit about your recent travels? And really, since I met you 6 months ago, you have been pretty much in every corner of the world. I've never met anybody that travels really like you do. So can you tell us a little bit about the reason why people are directly saying, hey, Moriba, come here, talk with us, and tell us what it is that we need to do to solve these problems, because you've certainly been a busy man.
Yeah, no. So to be honest with you, I think the main driver is that there aren't a whole lot of people that are kind of in the technical weeds and have done kind of this work of actually tracking objects and know what real data smells and looks like and that sort of thing, that want to also take a step across the bridge and talk to the people that write policy, or that are into the space law, or are into the entrepreneurship of things, or the space tourism and that sort of thing. So scientists and engineers kind of want to be left alone. They tend to be introverts, and they don't want to make those connections. Whereas I realize that the only way to solve this problem is to do an all hands on deck, get everybody involved, and really try to build community and build bridges. And so I can tell you that this problem of orbital debris and the path that we're going upon, which is the number of things is increasing and we have no real way to clean these things up and that sort of thing, is not just a problem of the United States or any single nation. It's a global problem. It's an international problem. And so, as you can probably imagine, the United Nations is involved. The United Nations has an Office of Outer Space Activities, and within the UN, there's this Committee on Peaceful Uses of Outer Space, which is now in the final stages of putting together some guidelines to help the long-term sustainability of space activities and the preservation of the space environment. So there's upwards of 60 spacefaring nations now Started off with just 3, right? As like the U.S., China, Russia. Well, now there's upwards of 60 nations considered spacefaring nations, and they're all playing around up there or have dependencies on things in space. And so they all get to weigh in, and by consensus, that's how things get passed at this Committee on Peaceful Uses of Outer Space. And so the UN really cares about making sure that that space environment can be used for peaceful purposes and future generations can have use of it, because so much of our lives these days is kind of entrenched in these dependencies. I mean, we all have cell phones that have GPS, and these things kind of tell us where we're located and how to get from point A to point B. Air traffic control systems rely on satellite positioning, navigation, and timing services. Banking systems now route things through satellites, TV, weather. So you name it, we have a lot of dependencies on space services and capabilities. And the interesting thing that people just don't even realize, aside from the number of objects, is that none of these services and capabilities are guaranteed to work. There's no space cop there's no sheriff in space that's trying to monitor everybody's behavior and activity and make sure that everybody's playing nicely and nobody's trying to do anything to anybody else, or that even due to unintentional causes that things can be disrupted or can be completely destroyed. So the fact that none of these things are protected and we have so much reliance on them, wow, that makes people all over the world pretty nervous.
And that makes sense. And obviously you're somebody that's trying to find solutions to these problems. Last time that we spoke, you kind of detailed a little bit of as far off as a 10-year goal of this. So what are you really looking at in trying to find solutions for these in the next 5 years? What are your goals for the next 5 years and 10 years? And is there anything the average person can do to be involved to kind of help fix this? Or maybe even some people that are, already right now they're in the beginnings of their science career, but maybe they want to help in, 4 years, 6 years, 8 years. What is it that we're kind of looking at? What's the long-term plan?
Absolutely. So I think the near term, the biggest obstacle to really being able to understand the real magnitude of the problem that we're facing is that we don't, as a global community, we do not do a good job in sharing data. So, I mean, the U.S. Strategic Command, they have these data sharing agreements with a wide variety of countries, but the data that Strategic Command shares are things derived from actual sensor observation, sensor measurement. So, they collect data, sensor measurements through this thing called the Space Surveillance Network that's comprised of radars and telescopes distributed around the globe, and they track these things, and then they provide services to people for orbital safety to say, hey, based on what we think we understand about what's going on in space, it looks like 3 days from now, your object is going to come very close to this thing, and you figure out what you want to do with that sort of information, because Stratcom is not a regulatory entity, but the FAA, the Federal Aviation Administration, is, which is, I can tell you right now that the U.S. government is really making a push to migrate a lot of these space traffic monitoring and management type of activities that the Department of Defense has done just historically, try to migrate that from the DoD, Department of Defense, to the Department of Transportation, which would fall in the hands of the Federal Aviation Administration. So there's actually talks right now going on that. If you look at spacenews.com, you'll see there was an event the past 2 days that I was actually physically at in Washington, D.C., where Dr. George Neild, who kind of leads this commercial space transportation office in the FAA, he gave some very good remarks about kind of the plan that FAA has moving forward to do this space traffic management type activity. But back to what's the kind of near-term goal, my goal is being able to get as many observations as possible in a common pool, in a common bucket that can be shared with as many people as possible. Because the thing is, if Group A has their own sensors, but they don't share their sensor data with Group B, and Group B has their own, and that sort of thing, everybody is trying to infer something about what's going on in space with incomplete data. And so the things that they can arrive at, the conclusions that they can derive from that, are going to be a lot less meaningful than if everybody combined this data set together in a kind of a big data analytics kind of fashion and just mined this really huge, large amount of disparate information so that people could say, okay, based on all the data possible, what is the answer and how are things behaving? So I think challenge number one, try to get people to collaborate a bit more. I'm certainly pushing strongly for a common pool of actual observations, not things that people inferred and say, okay, yeah, I think it's there and I'm going to tell you where it's at. No, you arrived at that conclusion by analyzing actual measurements, actual detections of objects. That's the raw kind of form of information. Put all that stuff together because that's what you need to do to start asking questions of all the data to try to see what you can understand. So that's thing number one, in my opinion. Thing number two is once you can get a large amount of people evaluating this really large data set, then we're going to start seeing things like, oh, turns out that these objects behave in this way, and that's very different than how these objects behave, and that sort of thing, and really understanding kind of more accurately how these things are interacting and that sort of thing. And once you can do that, then you can start talking about making kind of regulations and rules of the road. And just like there's, you know, rules of the road for driving, and there's kind of these rules for navigating on the seas, and there's similar rules for aircraft. You know, if two things are coming heading in the same, you know, going to have a head-on collision, both people like turn right or whatever. So we don't have those sorts of rules of the road for orbital safety because we don't fully understand everything that's going on in space, and we don't even know all the requirements to make sure that people can operate safely in space. I mean, somebody that has a CubeSat probably needs different kind of safety requirements than somebody who has a big satellite that has really huge thrusters, and different than somebody who has a medium-sized satellite with electric propulsion. So the thing is, we can't have just one rule for everything because there are many different types of objects in space. So we need to be more surgical, but that can only come as a consequence of a kind of a global scientific exercise of data exploitation.
Moriba, you are certainly passionate about what you talk about, and I think it's amazing to see somebody elaborate on these things that nobody else really talks about. Before I met you and kind of heard about what you guys were doing, as much as I sit and read as much science and space news as I can, this was something that I had never heard of. You know, it had to really come from you. And it's good that you're out there, you know, kind of being the evangelist for something that's extremely important. And it's especially important to people that, again, like we mentioned earlier, Jeff Bezos wants millions of people in space, and we want to kind of go to Mars. It's incredibly important to kind of figure these out. And it kind of got into a little, you know, like you said, you know, don't want to be alarmist, but a realist. So I figure we can kind of back out a little bit and do something a little bit more lighthearted. Can you tell us a little bit about some of the Mars missions that you did in your earlier career and working for JPL? That just sounds amazing to be, you know, that was kind of breaking ground on some really amazing things. You know, we've learned a lot from those missions. So could you tell us a little bit more about that?
Yeah, so the time at JPL was time extremely well spent. It basically seeded the foundation of my career as an astrodynamicist and really understanding how the space environment interacting with objects really drives their behavior. And I think, you know, the most awesome part of working Mars missions, aside from working with, you know, great people and actually getting objects all the way to the red planet, is like aerobraking. You know, for a couple of these orbiter missions like Mars Odyssey and Mars Reconnaissance Orbiter, those missions utilize this technique called aerobraking to save propellant. So aerobraking is all about, you know, using the atmosphere and the atmospheric dynamics, the fact that, you know, just like when you're in your car and you put the window down, you put your hand out the window and you can feel the resistance of the air pushing your hand kind of back. Something kind of like that with spacecraft, that you can utilize the atmosphere at Mars to kind of bleed energy out of the orbit, and you can actually save quite a bit of propellant. So it's a great technique, but the thing is, it's very manpower intensive. 24 hours a day, 7 days a week, kind of operations tempo. And so one of the things that I worked on, which I really cherished, was which ended up being my PhD work, was, is there a way that we can capitalize on measurements taken on board of these satellites such that maybe we could automate these aerobraking operations in some way? And so it turns out that these satellites carry inertial measurement units on board, and these inertial measurement units have these things called accelerometers and these things called gyroscopes. And the accelerometers pretty much sense contact forces. So it's like if if all of a sudden, if you were standing someplace and somebody kind of nudged you, the accelerometer could measure that nudge. It's what we have in these kind of interesting watches nowadays, where it measures your steps and tells you, what your physical activity is. These watches have accelerometers in them as well, and that kind of is a feedback mechanism to say what kind of contact forces are you experiencing throughout your day. So anyway, so these satellites have that, and atmospheric drag, that whole resistance thing that I talked about, those are contact forces, and these accelerometers can measure, how much resistance, and for lack of a better term, these satellites are experiencing. And the gyroscopes are measuring kind of angular rotational information. How is the thing oriented? And so I was able to take advantage of both of those measurements, as well as thruster activity of the satellite, and I came up with a method that can fuse all those data together and can give you a near real-time estimate, near real-time knowledge of how the atmosphere is influencing the satellite, to be able to even predict kind of where that satellite is going to be the next time it comes into contact with the Mars atmosphere. And aerobraking is one of these things where they use what are called it's a corridor. You don't want to go too deep into the atmosphere, because then you could could damage the satellite. Too much heat, the satellite could be very damaged. And the interesting thing too is that solar cell material is glued onto the panels, and so if the thing experiences too much heat, you could actually kind of make these things get unglued even. And so you don't want to go too deep in the atmosphere, but if you go not deep enough, then you're not bleeding energy from the orbit quickly enough to shrink the orbit down to its science mission size. And so it's kind of like there's this Goldilocks, there's this not too high, not too low, but just right place in the atmosphere where this thing goes through. And so, my PhD dissertation that takes into account these different data collected on board, I was able to demonstrate with real data that it's completely possible to compute these things on board and save manpower for future missions during aerobrake. And I was given a NASA Space Act Award because of that work. So it was definitely recognized for being quite excellent. And not to toot my own horn, but yeah, that was kind of the pinnacle of the stuff that I was able to do at JPL.
And but that's amazing though. I mean, you obviously, it seems like you earned it, because you were talking about just the manpower that went into trying to do it, but until you started figuring out those calculations and kind of putting all of that together. And so I mean, Mars is difficult. Space is difficult. There's a lot we're talking about, especially these days. And one of the things that we talked about on a phone call we had some months ago was kind of the idea of a GPS system around Mars, and the possibility of what you can kind of get into with that, and what would we need it, when would we need it, what kind of things it would take to do it. And so if we can talk maybe a little bit about that, and kind of what it's going to take to make sure that we're set up right when we finally get to the planet. And not only that, but to make sure that we don't make the mistakes we've made here with all the junk that we have in space now. There's a lot of things that have went into orbit around Mars, and especially crashed into Mars, as we saw this week. And getting to Mars is hard. So kind of if we can go some of the ideas that go into that GPS system, and avoiding the problems that we've had in the past here.
Right. So interestingly enough, one of the first ideas about having some sort of position navigation and timing assistance at Mars was some work that I actually participated while at JPL. There's a gentleman, Joe Gwynn. He's currently the section manager for the navigation mission design section, and he was my direct supervisor. But when I got to JPL in the late 90s, our work was kind of the seedling for this idea of a network at Mars. In fact, if you kind of Google Mars network, you'll find the papers on that, which were the initial ones that came up with this concept. And so the thing about this would be to, instead of having to burden all these satellites that we send there with having to establish direct contact with the Earth and direct communications, you could have you could send a couple of these dedicated things to Mars that would have these navigation packages, position navigation and timing packages, that could now serve as a relay to things that would either orbit the planet or make it all the way to the surface, and therefore kind of unburden those things from having this really huge communications package to get, spend a lot of power to get all that stuff back to Earth. They could just relay that stuff to this Mars network, and then through Mars network that could be relayed back to the Earth. And also these things could kind of provide kind of beacon type information so that other things could navigate around the planet based on where these things are located in a similar fashion to global navigation satellite systems.
And then, see, that's an incredible jump forward we're looking at with everything that's going to be going on Mars. And just to kind of wrap things up, and we appreciate your time today, we really kind of want to talk about maybe some advice that you have for people that are just getting started in the space and astronomy world, and maybe some things that you wish that you knew whenever you first got started, some things that you could have avoided that would have made it a little easier for you. So just some final words of advice.
Yeah, so I think my advice is the following. The space world tends to be saturated with quite a few people that think extremely highly of themselves. And listen, I mean, there are big egos everywhere in this kind of community. And I think the thing that I want to tell people is, don't be afraid or let yourself be intimidated by big names in the community. We need help. We need your help. If you have the enthusiasm and you're hungry for it, that takes you most of the way there. I can tell you personally, I wasn't this kind of straight A student all through school. I struggled. I had to stay up till 1, 3 o'clock in the morning doing calculus problems and trying to figure this stuff out. But it's something that I was just driven to do. And so what I want to tell people is, there's plenty of places in this community for you to make a contribution, and don't let any single person make you think that that you don't have something to contribute or that you can't do it. It's all pretty much up to you. The other thing too that I'd like to kind of give as some advice is, you've got to really seek out kind of opportunities, and just don't wait for things to happen, but try to create those. Try to meet the people. You, for instance, you're a great example of that. I mean, from the moment I met you, you got big energy. You're a smart guy. You just go out there and you engage. And so it takes doing that sort of engagement. And I guess, maybe a last thing is, unfortunately, our educational system is set up with these sorts of, you got a final, and the final's worth 30% of the grade, and people are so focused on the grades and not enough on learning. And I think the focus needs to shift from, how do I maximize my grades to how do I maximize the learning? Because I've seen many people go through school that have come out with very high GPAs, and you'd be amazed at how much they don't know, because they don't remember, because they memorize things instead of really trying to learn how things are and what's the relationship between things and what are some fundamental concepts and principles. And so I would really ask people, don't focus on the grades, focus more on learning it, on understanding it, and the grades will kind of, fall where they may. So I think those would be the things that I would try to tell people coming up is, you've got something to contribute no matter what path of life you're in. be hungry, pursue it. Don't let anybody tell you anything differently, and really, never lose that curiosity to learn and understand things, and focus on that. And I think the path will make itself very clear.
Thank you for those inspiring words, and we appreciate your time. I know that you're always busy and you're somewhere else again, so you're always all over the place. And a quick congratulations to you. I know you got another little one on the way, so that's awesome. Congratulations to you and your family, and I look forward to the next time we see each other. Thank you so much for your time today.
All right, thanks for having me. Love it.